Yeah. So
So the power
I don't
went out.
know if it's like related to all the rain or something like that, but
Yeah, probably.
we'll blame it. So sorry, I meant to get the permission form for Canada's Wonderland out to you, but I do actually have that now.
Okay.
In PDF form.
All right. Well, I can print that off whenever.
I'll send it out to you.
Sounds good.
Okay, so we're going to jump right into this whole scalar equation of the line thing.
Okay.
There's nothing too earth-shattering. We're going to look at ways we can use sort of the direction vector and the normal vector to establish the scalar equation of the line.
Okay.
So it starts out with this magical puzzle. So I have it in y equals mx plus b format here. Y equals 2/3 x plus 2. And I've converted it to scalar form. Haha. Without saying how I did that. My guess is you can probably guess.
Yeah. Take away the. Wait, hold on. Is that an arrow? Why? Or no, it's just a +3.
Oh yeah. Are you making fun of my
just,
+3s?
Yeah, I gotcha. Nope. Yeah. So you would multiply everything by 3, and then solve for 0. Basically, you set the one side to 0.
Yeah, that's right. Yeah. Isolate everything over on the other side. And it's kind of like, remember in grade 9, we did that thing, we called it the standard form of the line.
Mm-hmm.
There used to be this, I don't know if it matters or not, there used to be this different extra thing where the coefficient in front of the x term had to be positive. I don't think it matters for the scalar form of the line.
Yeah, I've always heard that everything, it has to be positive and it has to be not a fraction.
Yes. Not a fraction is definitely all positive.
But I've had everything be positive, or well, there's been negative things, and it seems to work fine. So I don't know.
Yeah. I think it's just people mostly being high maintenance. Okay. We're going to talk about the direction vector, and then we're going to talk about the normal vector, and we're going to see how it's related to the scalar equation. So y equals 2/3 x plus 3. What is the direction vector? A direction vector, probably the simplest direction vector for that line.
Hold on. Oh, sorry. It'd be 2/3 direction vector is the.
So the direction vector is basically just the one that goes in the direction of the line. So if this was my line, and this particular one has a y-intercept of 3, this slope tells me every time I go over 3, I go up 2. Yeah, that's right. Oh, I shouldn't maybe do that. Okay, so Lindsay's, she's practically bursting here. She wants to say what the direction vector is. And so basically, the direction vector for this one is, did I get it right? Because I got it backwards before. So the direction vector is 3, 2.
Yep.
Okay, makes sense, right? That vector is going to run all along that line. What is a normal vector? And so I guess I should say that's a direction vector, but what's a normal vector? In other words, when we say normal for vectors, we mean perpendicular, which is kind of funny.
Be the negative reciprocal of the slope, would it be? So then -3/2, or sorry, 3 and then comma 2.
Yeah, pretty close.
Oh.
-2/3.
Yeah, I did. Okay, yeah.
Yeah. Yeah, so once again, like once you take the reciprocal, the x and y's change, and then you change the sign there. Okay. So let's do this one right here. What is so y equals -4/3 x minus 2. What is the scalar version of this y equals mx plus b equation.
Oh, sorry, that would be 0 equals,
That's what I do. Start with the easy stuff.
yep, negative 3y. Or can you
Yep.
start with that? Might as well. Subtract 4x. Subtract, or yeah, probably.
Yeah, now, what do we want to do? I would do positive. I would actually do 4x plus 3y plus 2.
Wait, do we have to?
Lindsay's
multiply?
saying no.
There's something more you have to do. Yeah, there, okay. 6.
Okay. All right. There we go. Save the day again.
Yep, then you just change it all up. Okay, gotcha.
All right. What's the direction vector for this one?
3, common negative 4.
And what about the normal vector?
4, comma 3.
Perfect. Yeah.
I see.
Okay. Now the last part of this exercise, you're supposed to try and figure out how the normal vector is related to the scalar equation of the line.
All right.
So notice the 4 here shows up in front of the x there, and the 3 there shows up in front of the y there. And so as it turns out, whenever you have a normal vector, the x of the normal vector shows up as the a in this equation, and the y component of the normal vector shows up as the b. And then there's a final part that you need to figure out. But the normal vector is going to show up as the coefficients in that scalar equation.
Okay.
Let's see. So just for fun, I'm going to take this. I'm going to take this equation and I'm going to turn it into just give its vector form. And for its vector form, we have a position vector, and then we add some parameter t times whatever the direction vector is. And so I'm going to pick a position on the line, and then I'm going to add on t times whatever my direction vector is. And so I'm going to take a nice, easy spot in this case on this line. I'm going to choose the y-intercept. And so there is a possible vector equation for that line. And I've chosen my position vector just because it was easy. I chose the y-intercept, and then t times the direction vector. And down here, I'm going to do the same thing. This is going to be t times the direction vector, which is 3, -4. And I'm going to take my position as 0, -2. So I've just switched from y equals mx plus b, gone over to scalar. Then I've headed down here into my vector equation. So I'm just going to go into one of those nice show that. Show that the scalar equation with normal vector AB. And so we're generalizing this result over here where we see the normal vector, the x and y components show up as my coefficients. So if it has a normal vector AB, has the equation in general form ax plus by plus c equals 0. C is some constant. And so if we're looking at Cartesian plane, we have a line. That line goes through some fixed point x naught, y naught. So this is like my position vector. And it has a direction vector that ends us with a tip here at, in general, x and y. So my direction vector is x minus x naught, y minus y naught. Like, why not? Why wouldn't it be? My normal vector is AB. Okay. What do you think the dot product is between the direction vector on this line and the normal vector to this line? What should the dot product be?
0.
It should be 0, exactly. So when I do the dot product of this direction vector with this normal vector, I should get 0 by definition.
Interesting. Okay, so
we go AB dot x minus x naught, y minus y naught is equal to 0. I love using y naught. So we get the dot product is going to be a x minus x naught plus b y minus y naught equals 0, which becomes ax minus ax naught plus bx minus bx naught, which is equal to 0. And I'm almost to the result that I was after. Oh, yeah. Fortunately, I wrote x instead of y's, yeah. I even liked saying why not, so you'd wonder why I quit doing it partway through. There we go. Okay. So now I have ax plus by minus this and part right here. This is always this is just a constant. This comes out to some number because I've chosen a position on the line. I think for this example, I would have liked to have tried it where I choose a specific point like 3, 4.
Mm-hmm.
And then you would see that, yeah, this is really just a number based on whatever A and B is. Anyways, this just becomes a constant, so we just give it the number C. We symbolize it as C. Okay? So basically all this is showing you is that if A and B is my normal vector, yes, A and B show up here in the scalar equation of the line. So that's the whole point of that exercise.
Okay, I see.
It's kind of nice just to say, yeah, here's another way we can use the dot product.
All right.
And occasionally this is going to be one of the keys to problem solving where you're going to say, oh yeah, the dot product of this vector and the normal vector is going to be equal to 0.
I see.
And you might be able to solve for a few parameters that way.
That makes sense.
Okay. So what's the scalar form of the line through? I'm going to put this through 4 and 3. So there's a position, there's a place on the line, a point on the line, and it has the normal vector to -3. And I can tell you right now, there are a lot of different ways of doing this.
Mm-hmm.
We could actually do it just the way we did it last time. And because we have numbers both for the normal vector and for a position vector, we would actually end up with being able to calculate what that C is. But that seems like a lot of work to me. Any better suggestions how we could do this quickly and easily?
Just
How much can you tell me about the scalar equation right now, just looking at it?
scalar equation. So we know the, well, we would know the A and B.
Perfect. Yes. And so this is going to be 2x minus 3y plus, and G, I don't know C.
Is it plus or minus 3?
Oh, yeah, sorry. I said plus, but my right hand did minus, so I think we're okay. Did I get it right? All right. Jeff, you're looking doubtful.
Is it plus or minus?
Right there?
Yeah,
That's a minus.
okay. Should it still be minus in the equation? Yeah.
Yeah, because it's the normal vector.
Yep.
Makes
right.
sense?
Yep. No, it does.
Okay. All right.
Afternoon.
The last thing we have to do is figure out what C is. How are we going to do that? Lindsay is poking her pen in the air at the number 4 and 3.
Yeah.
She wants to put it in for X and Y, I think.
That makes sense.
Lindsay's pretty saucy today, actually, just for the record. 8 minus 9 plus C is equal to 0. So C is equal to 1. And so this is 2x minus 3y plus 1 is equal to 0. Okay, and in the magnificent preamble that I was preparing, I was actually going to demonstrate that the angle between two normal vectors, so if you've got two lines and you've got two normal vectors, you can find the angle between the lines by finding the angle between the normal vectors. I was going to do that.
I see.
So anyway, do you believe me? Let's put it that way. Do you believe me if I told you that?
Yeah, I think so.
Yes. I think if you can kind of imagine two lines and, you know, if you put the normals on them. So if this was line 1 and this was line 2, you know, if this was the normal vector to line 1 right here, and that was the normal vector, oh, let me put that. If this was the normal vector to line 2, or sorry, I shouldn't say the normal vector because there's way more than just one normal vector, that this angle right here is equal to that angle right there.
Oh.
Okay. So the angle between normal vectors is equal to the angle between lines. Okay, and this becomes a kind of a neat trick that we get to use later on when we're dealing with things like planes. So if we want to find the angle between planes, we might, in some clever way, find the normals Find the angle between the normals. All right, so the problem looks like this. Oh, the power just flickered a little bit. Call the buses. Take everyone home. So that's easy. I mean, finding the normal vectors is easy. First normal vector, -2, 5. The second normal vector, 6 and 1. And we can find this angle theta using the dot product. That's right.
You'll get it.
Yeah. Okay. So the cosine of theta is equal to.
And nope, no, sorry.
Yes, you're right. N1 dot N2.
Over the magnitude of.
Perfect.
Both of them.
Yes.
Yeah.
Somebody studied on Friday.
A little.
So theta is equal to arc cos. Oh no, I have to figure out my magnitudes. Oh well, that's okay. -2, 5 dot 6, 1, because somebody borrowed my calculator. Okay. Square root 29 times square root 37. Inverse cosine of -12 plus 5. -12 plus 5, oh, -7. Hey, Jeff,
Hey,
can you hear us again?
I can hear you, but I can't see you.
Oh, okay. Well, can you see me now? Because actually, we did, in fact, make it pretty much to the end of the lesson.
There we go. Yeah, no, I was thinking.
Yeah.
So. Did the power go
Yeah,
out?
so that's about it. Lindsay's feverishly working this out right now. The square root of 29 is about 5.3, and the square root of 37 is about 6 point, I'm going to say it's 6. So this is -7 over like about 30. It's about 1/5. So this is going to be about 70 degrees. That's my guess.
Ready.
Okay, I'll do. Jeez. Oh, but then it's -7. Oh, -7 divided by square root 29 divided by, uh-oh, I should have done this all on one line because it's just going to get that much boring. Negative 2.136.
Yep.
Sorry, 0.2136. 102 degrees.
Really?
Yeah. Well, because it's negative. So it's in the second quadrant.
Oh, I gotcha.
And so one of the angles between those two lines is 102. But there is a second acute angle, which is going to be 180 minus 102, which is going to be 78. Okay. I said 70, so I was pretty close. All right. And that is that. So scalar form of the line, basically, it's just, what we called in grade 9, we called it the standard form of the line.
Mm-hmm.
Coefficients a and b of the scalar form of the line are the same as the normal vector. And you can use the fact that the dot product is 0 to help you solve certain parts of those equations. And you can use the cosine rule for dot product to find the angle between lines based on the normals.
Okay.
That's that. All right. Any questions?
Nothing right away, but are there homework questions for this lesson?
Yeah, so I'll just put up, Lindsay's saying no, but that's because she's saucy. Yeah. Yeah, so the homework questions, I'll put them up. They're all pretty easy. Like this part, this last thing that we did is maybe about as complicated as it gets. So
All right, I should probably just go through some repetition with it.
I'll put them up. All that darned no internet stuff.
Oh, right.
Yeah. Okay. Well, thanks, Jeff.
Yeah, thanks.
We'll see you tomorrow.
See you then.